Hello students, welcome to Shri classes. We'll begin with chapter number 13, physics chapter, magnetic effects of electric current. So let us see the chapter flow. Magnetic field and field lines. Magnetic field due to a current carrying conductor. Oersted's experiment forms the basis for this chapter, which establishes the relationship between electricity and magnetism. Magnetic field due to a current through a straight conductor, magnetic field due to a current through a circular loop, and magnetic field due to a current through a solenoid. And of course, with straight conductor, there is going to be a right hand thumb rule which we are going to study. And then comes force on a current carrying conductor in a magnetic field. Whenever a current carrying conductor is placed inside a magnetic field, it experiences a force. And that part we are studying. Based on that principle, electric motor we are studying. And finally, the electromagnetic induction, where Faraday's laws of electromagnetic inductions will be discussed. And based on that one, electrical generator works. But the principle of electrical generator will be studied, but not the electrical generators. So generator part is deleted from your current syllabus. Therefore, we may not discuss this electric generator, but all these points can be discussed. So let us start with what is a magnet, magnetic substance, and then we'll watch a couple of videos, and then we'll look into Oersted's experiment, which is the basis for this chapter. I hope you have understood the chapter flow. Let's get back to the first section, magnetic field and field lines. So, as this chapter talks about magnetic field and field lines, we should know something little bit about the bar magnet, how to plot the magnetic field lines, the definition of magnetic field lines, and what is magnetic field. First of all, magnet, you must have seen in your household the magnets. Probably you must have seen the circular disc shaped magnets, but of course you have bar magnets, horseshoe magnets, etc. What is a magnet? A magnet is a substance having both attractive and directive property. It will attract the magnetic substances. For example, if iron nail is brought near the magnet, it will attract. Also, it has got a directive property. If I suspend a bar magnet freely with a silk thread, it will point towards the north of the or the magnet will stand in the direction of geographical north and south directions. The pole or the end that shows the geographical north is called a north seeking pole or a north of the magnet, and the end that points towards the geographical south is called the south pole of the bar magnet. Okay, and therefore it has a directive property also. You understood? Next, classification of the magnets, mainly natural magnets and artificial magnets. Naturally available magnets are the lodestone Fe2O3 or a basalt, which is a rock basically, and it is weaker in strength and no definite shape. Of course, naturally occurring magnets, they have a weaker strength. The strength of the magnet is measured in terms of magnetic field, that is a Tesla. So for naturally occurring magnets, the strength is very weak, very weak magnets, and there is no definite shape because these are naturally occurring. Whereas artificial magnets, man-made magnets can be a bar magnet, horseshoe magnet, etc. And these magnets can be made to the required strength and can be made in different shapes and sizes also. Of course, the polarity also can be changed because every magnet will have a north pole and a south pole. You got it? And one more property you should know when I say attractive property. When two magnets are brought together, then there is a repulsive force or attractive force. The like poles will repel, unlike poles will attract. That you know in magnet. If required, that also we'll discuss later. So this is a bit about magnet and their classification. Next is magnetic substances. What are magnetic substances? Substances from which the magnets can be made are called magnetic substances. Iron, nickel, cobalt, alnico. Alnico is an alloy which is aluminum, nickel and cobalt alloy. And there are types of magnets. You can have a bar magnet, you can have a horseshoe magnet, you can have a circular disc shaped magnet, And of course, magnetic needle and magnetic compass are, to be precise, not the types of magnets, but of course these are also made up of magnets. Therefore, I have taken here magnetic needle and magnetic compass. These are the instruments basically that are used to find out the magnetic meridians of the earth, or approximately the geographical north and south poles of the earth. So these are the two instruments that are used. So what else is there? Let's see next slide. Yeah, here this slide talks about magnetic field and the field lines. We should know what is magnetic field and field lines. We should know very clearly. Here it is a bar magnet, and when the iron filings are sprinkled over the bar magnet, see, if you directly sprinkle the iron filings, it will attract them. You may not be able to find out these lines over here. Can you find all these lines over here? The iron filings have aligned themselves to form these arcs here. Those are called field lines. So what is that is generally done is, say for example, if there is a magnet, what I can do is keep the magnet at the bottom and keep one paper thin sheet over which iron filings can be sprinkled. You got it? In that case, you can find that the iron filing will get realigned themselves. The filings will get realigned or get arranged along the magnetic field lines. So the lines which we see over here are the magnetic field lines. Here you can see very clearly it is mentioned. The field lines are also mentioned with directions. So what is magnetic field and field lines? We should know. Magnetic field is the region surrounding the magnet where another magnet can experience a force. Do you understand? A region, the area, or not area, it is a region, it is a three-dimensional. Please remember, it is a three-dimensional. The region surrounding a magnet where another magnet can experience a force is called the magnetic field. A representation of the magnetic field is by means of magnetic field lines. One can plot these magnetic field lines using the compass, instrument compass. How to plot? We'll have a look at a small video there. And this is how the magnetic field lines look. From this diagram, I can say these field lines emerge from the north pole, because every magnet has a north pole and south pole. There is no magnet where unipolarity magnet is available. No. Every magnet, if you make a small pieces out of this magnet also, every magnet will have two poles. One is a north pole, one is the south pole. So every magnet is a double polarity item. So it will not have a single polarity. Polarity means north and pole, south poles are called polarities or the poles of the magnet. Here the field lines emerge from the north and merge into the south. Emerge means they come out of the north, and merge into the south means they enter into the south. Also, these field lines are not discontinuous. The field lines are continuous over here, meaning these are closed curves, meaning externally the field lines are from north to south, but again internally from south to north. That is how the field lines will be there. We'll see the video lecture where how to plot these magnetic field lines and how to identify the direction. Okay, and this is the diagram given in your textbook to plot, how to plot the magnetic field lines using the magnetic compass. That we'll see the video lecture. Okay, so now let's have a look at the video lecture, and then let me check what is the next this thing. There is a definition for magnetic field and magnetic field lines. We'll finish this and then we'll watch the video. Magnetic field, it can be taken closer here, close up. See, you have to pause the video and note down, make a notes. Okay, I will not be telling to note down this, that and all. Dear students, ensure that you pause the video whenever a new slide appears and make a proper notes out of that. So The definition of magnetic field and magnetic field lines we are going to see here, and then we'll go to a couple of video clippings, then come back to the PPT. What is magnetic field? The region surrounding the magnet in which force of the magnet can be detected by another magnet is called a magnetic field. In a magnetic field, the compass needle experiences a force and thereby gets deflected. So the region surrounding the magnet in which another magnet experiences a force is called the magnetic field. And why the magnetic needle or a compass deflects? Because the compass needle or simply the needle is also made up of a magnet, and therefore whenever that magnet is brought in the vicinity of the magnet, it will experience a force and gets deflected. In the absence of magnetic field, the magnetic compass or the needle points towards approximately the geographical north and geographical south poles. Okay. So next is magnetic field lines. What are magnetic field lines? Representation of a magnetic field. One way of representation of the magnetic field is called magnetic field lines. Not one way, it is the way to represent the magnetic field. So magnetic field lines are the paths along which a hypothetical north pole tends to move. After watching video, I'll read this statement once again. Magnetic field is represented by a field lines along which the iron filings align themselves. I hope you have understood 2 points over here. The region surrounding the magnet, which is called magnetic field, and which is represented by magnetic field lines. The direction is from north to south externally and internally from south to north. And how to plot this, we'll watch the videos now. Okay, well, I'll take just a pause here and then we'll look at the videos. We'll have a look at the video clipping now.
Hi there, and welcome to Mr. Musselman's online teacher workshop. Magnetic fields can be tough for students to conceptualize, but with the help of a magnet, a piece of clear glass or plastic, and iron shavings, you can be on your way to helping students better visualize the magnetic field all magnets create. Begin by placing the clear plastic or glass over a magnet. In this case, I used the cover of an old takeout tray. Carefully shake the iron filings out over the magnet and clear cover. You'll notice that as you shake, the filings will begin to arrange themselves almost magically across distinct lines. This is a result of the north and south poles of each shavings arranging themselves with the magnetic field. When done shaking, make sure kids observe the pattern both overhead and from the side. From the side, they'll observe that the field is three-dimensional, meaning the magnetic field extends in all directions from the North Pole and wraps back around to the South Pole. Consider trying this activity with a horseshoe or ring magnet to see how the fields are different than the bars. With the help of this activity, students should come to recognize that all magnetic materials create a magnetic field. That includes Earth's core. A diagram like this can also be used to see how well students understand that north and south poles attract and vice versa. Ask your students, why does the imaginary bar magnet inside the Earth appear to be upside down? Want to learn more? Visit us online at the Burlington Science Center blog or Facebook page. Thanks for joining us. See you soon!
It's probably safe to say that you have a very good idea of how the magnetic field of a bar magnet looks like. But do you know the 4 important properties of magnetic field lines? To find out, let's begin by plotting some magnetic field lines. We need a pen, plotting compass, and a magnet. My magnet doesn't tell me which is the North Pole and which is the South, but we'll find out soon. Place your magnet in the middle of the page and trace around it. Place place the plotting compass near the magnet. Mark the direction that the compass needle points by drawing a dot. After the first plot, move the compass so that the back of the needle lines up with the dot. Repeat this until you reach the end of the magnet. Join the points together to show a field line. I'll also draw an arrow here to show the direction that the needle is pointing in. I'll do all of the above again with another starting point. Looking at the field that we've plotted, we can figure out the four main properties of magnetic field lines. Number 1, magnetic field lines never cross each other, they never overlap. Number 2, they always point from the north pole of the magnet to its south pole. North into south, so that must mean that this is north and this is south. Number 3, they are continuous. The only reason these lines have been cropped out here is because I've simply run out of space. Number 4, where the lines are closer together, the magnetic force is the strongest, and that's at the poles of the magnets.
So from the picture it was very clear. Just a moment, let me wear this. Yeah, I think from those two video clippings, you are familiar with how to plot the magnetic field lines around a bar magnet using a compass. Compass is an instrument. When I say the needle points towards a particular direction, means the north pole of the compass is marked red and the direction of that is referred as the direction of the pointer. I hope you understand that. Okay. So next is these definitions. Here I said I'll get back to you once again with magnetic field lines. So magnetic field lines are the paths along which a hypothetical north pole tends to move. You got it? And magnetic field is represented by field lines along which the iron filings align themselves. This is what you have seen. Let me explain a little bit on the board and then I'll get back to the PPT once again. See, a couple of things which I would like to talk about. This is a bar magnet. I think let me draw a little bit down here. You have a north pole in this bar magnet and you have a south pole. Whenever, and you should also know that magnetic compass, see if this is a compass over here, generally the north pole of the compass is marked red. So this is called the pointer in the compass. The direction of the pointer means in a compass the direction indicated by the north pole of the compass. Do you understand? Direction of the pointer means direction of the north pole indicated by the pointer. Okay. So if this is a bar magnet over here, couple of properties let us see. If I take one more magnet over here, if this is north pole and south pole and north pole will repel. So like poles repel. There is a repulsion force between these. On the other hand, if I have two magnets, which is north pole and this is south pole, NS, SN, and here there exists the force of attraction over here. In this case, the field lines will be something like this. The field lines will be something like this, which we'll study later. But here there is a force of attraction. Here there is a force of attraction, and these are unlike poles. Unlike poles. So what I just wanted to say is, like poles repel and unlike poles attract each other. That is one property you must know. Also, while plotting the magnetic field lines, this is how it was plotted in the video. Just I would like to highlight about that, and then we'll go back to the PPT. See, if I keep something like this here in the vicinity, if I keep the compass needle, then the needle may show something like this. Mark this as a point here and shift this one. So if you keep once again over here, it may point something like this. So keep it over here, once again the compass, it may point something like this. So shift the compass, it may point something like this. You got it? So this is how the direction of the magnetic field lines. This is how we can observe. These are the compass which we have shifted and we have arrived at. Here from this diagram it is very clear that wherever the direction is pointed by the compass, towards that direction the field line moves. Meaning in this one the field line is like this. What is the direction? This way, north to south. You can shift the position and obtain few more field lines, something like this. Okay, this is how you can obtain. I hope you are able to understand. Okay. So in a bar magnet, what is important to understand is, what is the direction of the magnetic field line? Direction of the magnetic field line is the direction of the pointer of the direction of the pointer of the compass, and generally the direction is the direction of the field line is tangent to the curve at a particular point. Means if I ask you to find out what is the direction of the field line at this point, if I ask you, then you must know that the direction at this point of the magnetic field line, the direction of the magnetic field line at this point is not this way, this way. Direction at this point is tangent to this curve, like this. This is a tangent here. What is the direction of the field line at this point? This is once again tangent to the field lines. What is the direction at this point? Once again here it is tangent to the field line. So direction of the field line at any particular point is tangent to that point, tangent to that curve at that point, and it is from north to south. That is also very important. So let us now have a look at the PPT once again. What are the properties of these field lines? These are called the field lines. They move from north to, that also I will indicate here itself once again. Suppose this is a bar magnet, north and south. The field lines are closed continuous lines. Another two lines I will take. North to south. They emerge from the north and they merge into the south. They emerge from north and merge into the south. But these are closed curves. Remember, these are closed curves. So north south, north to south. This is also north to south. And inside, look at this mark the direction of the field lines inside. Yeah, inside it is towards that, south to north. So direction of field lines are externally north to south, internally south to north. Field lines emerge from the north, field lines merge into the south. Field lines emerge from the north pole and field lines merge into the south pole. These things you must know. That's all about the magnet, and couple of things are there, magnetic field line properties, which we'll have a look at the PPT once again. So magnetic field lines. Magnetic field lines are the paths along which a hypothetical north pole tends to move. Why a hypothetical north pole tends to move? The magnetic compass needle will get deflected and it will point towards the north of it will point towards the south of the magnet, and therefore we say magnetic field lines are the paths along which a hypothetical north pole tends to move. That means pointer of the north pole of the compass gives the direction of the magnetic field lines. So make a note of all these things. Next, once again, direction of magnetic field lines or the magnetic field. As I said, magnetic field is a vector quantity. It has got both magnitude and direction, and the direction of the magnetic field at a point is given by the direction in which the north pole of the compass needle moves when placed at that point, and also it is tangent to the curve. Those 2 points you must remember. Then what is magnetic field? It is a vector quantity having both magnitude and direction. What are the units of magnetic field strength? SI units is Weber per square meter, or it is called a Tesla, and 1 Tesla is nothing but 1 newtons per ampere per meter. It is 1 Tesla is 1 Newton per ampere per meter. What about CGS units? Gauss, which is represented by capital G, and which is derived on the basis of the name of the scientist called Gauss. So 1 G is equal to 10 to the power minus 4 Tesla. You got it? So these are the SI units and the direction of the magnetic field. Make a proper note of all this. Here once again the picture of the bar magnet and the magnetic field lines are shown. Direction of magnetic field lines: externally north to south, internally south to north, explained already. And inside the magnetic field is uniform. The magnetic field strength is uniform. As we move away from the bar magnet, the magnetic field strength decreases. And also the density of the field lines is an indication of the magnetic field strength. Closer the field lines or denser the field lines, the strength of the magnetic field is more. Rarer the field lines, the magnetic field strength is less. What are the properties of magnetic field lines? Magnetic field lines are closed continuous curves. All these are closed and continuous curves. Magnetic field lines are directed from north to south externally and south to north internally. Magnetic field lines are never intersect. They never intersect. Why they never intersect, we'll see later. Magnetic field lines are crowded near the poles, hence the field strength is stronger at the poles. Here at the north and south pole, these field lines are crowded, meaning the density is more and hence the field strength is more. These are the 4 properties which you must know. Next is, here there is a question here, why no 2 field lines intersect each other? Very important, this question generally appears. See here, I'll explain this on the board and then it is better to understand. Let us consider a bar magnet. North, south. These are the field lines. Emerge out of the north, merge into the south. Question is, why 2 magnetic field lines never intersect each other? Say suppose somehow it got intersected like I'll use the colored pen here. Let us assume that this got intersected like this. Whether this is possible or not, we'll see. At the point of intersection, if I place a compass needle, what is your expectation? In which direction can you expect the needle to move at this point? For your information, if I keep the magnetic compass over here, and it will move like this, it will show like this. The direction of the pointer gives the direction of the magnetic field line. If I assume that the two lines intersect, then in which direction do you expect the magnetic needle to point? Definitely it has to point. Then tell me, can a magnetic needle of the compass point two directions like this and like this, tangent to this curve and tangent to this curve simultaneously at any point of time? Is it possible? Never possible, no? And therefore the two magnetic field lines never intersect. I hope you understood. For example, here also, if I keep the magnetic compass over here, where do you expect the needle to point out? Can it show like this or can it show like this? It is impossible for a needle to point towards two directions at any given point of time. It is not possible, and therefore we can conclude that two magnetic field lines never intersect. This has to get deflected. Why this has to get deflected? Because it is in the vicinity of the bar magnet. This magnetic compass needle experiences a force and it has to get deflected. And the direction of the field line is given by the direction of the pointer of the compass, which is marked red basically. So here if I keep over here, do you expect tangent to this curve or tangent to this curve? It is not possible. This compass cannot show two directions at any given point of time. Hence the conclusion that two magnetic field lines never intersect each other. I hope you have understood. Now let us look back at the slides PPT. Why no two field lines intersect each other? No two field lines are found to cross each other. If they did, it would mean that at the point of intersection, the compass needle would point towards two directions, which is not possible. Hence, no two field lines intersect each other. That should be your answer. This is taken from your textbook. Most important, you should know how to write answer for this question. Many times this question appears in the exam. Fine students, let me see what is the next slide now. Yes, we are going to start the chapter now. So for whatever we studied, it was a very basic of the bar magnet and the properties of the magnetic field and the magnetic field lines. Magnetic field due to a current carrying conductor. Before I start this one, we must discuss the effects of electric current, chemical effect of electric current, heating effect of electric current, and magnetic effect of electric current. So come with me now. Here we will see effects of electric current, chemical effect of electric current, which we have studied in electrolysis of water. Whenever electric current is passed through acidulated water, chemical reaction takes place, that is decomposition reaction, and water molecule will split into hydrogen and oxygen gas. So there we find the chemical effect of electric current. Similarly, in current electricity chapter, we found the heating effect of electric current. According to Joule's law of heating, whenever an electric current is made to pass through a purely resistive electric circuit, then the entire electrical energy will get converted into heat energy, and that is called the heating effect of electric current. In this chapter, we are going to study the magnetic effect of electric current. Meaning, if this is a conductor over here, if I pass current through this conductor behaves like a magnet. Meaning, a current carrying conductor produces a magnetic field. and the basis for this chapter is Oersted's experiment, and he was the first scientist to link the electricity and magnetism. So these are the effects of electric current. We are studying now magnetic effect of electric current, for which it is important to understand the Oersted's experiment. Okay, let's have a look at the PPT once again now. Hans Christian Oersted, he was one of the leading scientists of the 19th century. He played a crucial role in understanding electromagnetism, the relationship between electricity and magnetism. In 1820, he accidentally discovered that a compass needle got deflected when an electric current passed through a metallic wire placed nearby. Through this observation, Oersted showed that electricity and magnetism were related phenomena. His research later created technologies such as radio, television, and fiber optics. The unit of magnetic field strength is named the Oersted in his honor. So this is a brief history about Hans Christian Oersted, and his experiment forms the basis. In order to remember and understand his experiment, I have a small demonstration, and then we'll get back to the PPT once again. In order to understand Oersted's experiment, what is Oersted's experiment? A current carrying conductor produces a magnetic field. If this is a conductor, pass electric current, it behaves like a bar magnet. We have to understand one acronym, SNOW, S-N-O-W, to understand Oersted's experiment. What is the SNOW rule? It is not a rule, it is for our understanding. Something like, please stop calling me a zebra. I like him calling me me a sweet girl, Preeti, something like that, which we had designed for understanding the activity series, isn't it? Similar to that one, SNOW, what is the meaning of the SNOW here? Current passing from south to north in a conductor over the compass deflects the needle towards the west. S-N-O-W. If the current flows through a conductor from south to north, and if the conductor is placed over the compass, then the needle of the compass will deflect towards the west. Why the needle deflects? Because it experiences force. Why it experiences force? Because a current carrying conductor behaves like a magnet. So in the vicinity of one magnetic compass needle also experiences a force, and it deflects towards the west. So in order to understand, I have made one small thing. Let us assume here this is the conductor. Here this is the conductor. Okay, south, north, and the direction of this arrow indicates the direction of the current. If I flip this south to north, the direction is indicated by this arrow. I think if required, it can be, if I bring this closer to this, I think this is enough. Now we are able to clearly see this. I hope it is very clear now. So what is this basically? This is not a sheet of paper or a cardboard. It is a conductor for the time being. Okay, this is a metallic conductor. This end terminals will be connected to a battery in such a way that I can make the current to pass through from this end to this end by connecting positive terminal over here, or I can make the current to pass from this end to this end by connecting this to the positive terminal of the battery and this to the negative terminal of the battery, because current flows in an external circuit from positive terminal to the negative terminal, whereas electrons move from negative terminal to the positive terminal. So the direction of the current is opposite to the flow of electrons. That also we have revised now for the time being. Okay, so this is about the conductor. Here I have written SNOW. This is SNOW is to be read properly as current passing from south to north in a conductor over the compass deflects the needle towards the west. That is important. And what else? That's all in this. Next, here this is a magnetic needle or a compass needle. Here I hope you can clearly see is it perpendicular? Let me make it perpendicular once again. See here, this is the red part is the pointer of the needle, which is a north pole. This is a south pole of this needle, and here it is east and here it is west. For example, if this is the north, towards the right side of the north for me, towards you it is east, and away from you towards the board it is west, and this is south. Once again, north, towards you east, towards the board west, and towards me is the south. Freely suspend it now. This is freely suspended. Where do you expect it to move? We expect this to move and stabilize in the direction, in the geographical north. So this is the north here. It is pointed here. It has pointed towards the geographical north, and it is standing now. This is standing like this. So this is north. What you are seeing is towards you is east, and towards the board it is west, and this is south. I hope you are very clear with respect to the directions of this compass needle. If it is not clear, camera can be brought little bit front. Okay. Now what I will do here is, once this is balanced along the south north directions of the earth, it will stand like this. Now I will bring a conductor, and what I will make is, I will place the conductor over this. Is it clear? I am placing the conductor over the compass. Let the current, these end terminals are connected to the battery. Let me switch on. I have connected the battery terminal such that the current in the conductor flows from south to north. In this case, the moment I switch on, the conductor behaves like a magnet. It produces magnetic field, and this compass which is kept in the vicinity of the wire or the conductor below experiences a force, and according to Snow rule, it deflects towards the west like this, because east is towards you and west is towards the board. Once again, freely suspended magnet stands like this, pointing towards the north. Bring the conductor, align it along with the south-north direction. Make the terminals, connect the battery terminals in such a way that the current flows from south to north. The moment you switch on now, yes, the magnetic needle deflected. Switch off, comes back. Switch on, the magnetic needle deflects away from you towards the west. Switch off, it will go back and stand. Whenever you switch off, the conductor becomes non-magnetic. Whenever you switch on, the conductor becomes magnet, and the compass experiences the force and points towards the west. Isn't it? Now switch off. Okay, this is the situation. Can we change the direction of the current in the conductor now? It is in switch off condition. Both are like this. Can we switch off and can we change the direction of the current in the conductor? Yes. Let me flip. Yeah, check now. The current is moving from north to south. Correct? Earlier current was flowing from south to north, and now the current is moving from north to south because I have changed the battery terminals. In this case, this is a magnetic needle here, and I am holding the conductor like this. Current is moving from north to south, the direction of which is indicated on the conductor. Switch on. This is how the needle deflects. Now the needle has deflected towards you. Isn't it? Is it not? Because earlier the needle was deflecting towards that. Now the needle is deflecting towards you. You got it? Towards you. It is east. Because see here, E is written as east here. East is towards you. West is towards the board. Earlier it was deflecting towards the board. Now switch on like this. So if the current direction is reversed from north to south, then the needle of the compass deflects towards the east. What is the snow rule? Towards the west. If the current flows from south to north, but if it flows from north to south, the direction of the compass is getting reversed. Switch off like this. Switch on, it is deflecting towards the east here. Switch off like this. Once again, flip the direction of the current. Let the direction of the current flow in the conductor from south to north. Then the magnetic needle of the compass gets deflected towards the west, away from you. That is the west here. Switch off like this. Flip the direction of the current north to south. The deflection is observed in the opposite direction. Switch off, goes back. Once again, change the direction of the current. It will get deflected away from you towards the west. And this is how the deflection is taking place. I hope you have understood. Now, coming back to now, what I will do here is, earlier I kept this compass needle below and changed the direction of the current. Now, direction of the current in the metallic conductor is same, but the position of this compass I'll change. Once I'll keep like this below the conductor, and then I take over the conductor, below the conductor and over the conductor. Let me stick to the snow rule here. Let the current flow from south to north in the conductor and keep the magnetic needle at the bottom. Switch on towards the west. You got it? Switch off. It comes back to the north position. Shift the position of the compass above. Okay, I have shifted above now. Switch on. Direction of the current is same, indicated by the arrow on the conductor, which is on my left hand. This is the conductor. Switch on. Yeah, pointer is moving towards you. Means the direction of the pointer got reversed when it is brought above the conductor. Switch off, goes down. Now shift back. On, switch on. West. Switch off. North. Shift the position above the conductor. Switch on. East. Switch off. North. Bring back. That means here, why did I do all these things? I think now camera can be made to cover me also. So I think you can set it to the board width. Okay. So what is this? What is the meaning of this one is, if there is a current carrying conductor, it produces a magnetic field, and if the compass needle is brought in the vicinity of that one, it will experience a force, and therefore it is getting deflected. In which direction it is getting deflected is what we can remember it by snow rule, SNOW. We have to note down this one and understand. You have to note down. Why you have to note down is, dear students, there is going to be a 1 mark question based on this snow rule. Snow rule is not a rule. It is not given in the textbook. It is created by the Rachana Sagar book. Do you understand? He gives snow, including ICSE syllabus, Snow is the acronym by which you should be able to remember how the deflection of the magnetic needle takes place when it is brought in the vicinity of the current carrying conductor. I hope that is very clear. Now, I'll take you to the PPT, and one experiment is there. We'll try to identify in which direction the needle moves. That is more important there. So, Hans Christian Ørsted's experiment. This is what it is given. It is a conductor connected to a battery terminals, positive terminal and negative terminal. Therefore, the current flows from like this, from positive to the negative terminal. So the direction of the current is in this way. Here, whenever this magnetic compass is brought in the vicinity of this one, this will produce a magnetic field. Because this acts like a magnet, it will produce a magnetic field lines, and the needle will experience a force and it will get deflected. The needle of the compass will get deflected. And what is the direction of the magnetic field lines produced by this current carrying conductor? The direction of the magnetic field lines produced by this conductor is along the north pointer of the magnetic needle. Isn't it? That is what we have studied also. Okay. So let it be there for the time being. Let us go to one experiment here. here. See, dear students, snow rule I have written here also. This you can note it down. Snow means south to north over the compass towards the west. A current flowing from south to north in a conductor which is placed over the compass deflects the needle towards the west. That is the snow rule. This is the given diagram. Conductor is aligned along the south-north direction like this, and this conductor is connected to the battery terminals, positive this end, negative this end. So direction of the current is from like this. Current direction across this conductor is from north to south. Where do you expect this magnetic compass needle to move towards? North to south, towards the east, because snow is south to north towards the west. North to south, opposite direction, east. Therefore, this is east here. If the current flows from this end to this end, the needle of the compass, which is below this conductor, points towards the east here, and therefore this is how it has pointed out. Why it is shown north south here? Because this arrow generally points towards the north, geographical north, and therefore this is the north pole of this compass. The north, it is a pointer basically. So now pointer has pointed towards the east now because it is kept in the vicinity of the conductor that carries current. Now come to this diagram here. Now positive terminal is connected here and negative terminal is here. Current direction is this way, from south to north in this direction. If the current flows from south to north over the compass, the conductor is placed over the compass, above the compass, then the pointer should deflect towards the west here, and therefore this is coming towards the west. The deflection depends upon the amount of current. If you increase the current, see, if there is a smaller amount of current, then the deflection towards the west or the east is only slight. But if more current passes through, then the deflection will be almost perpendicular to its original direction at 90 degrees to the original direction. So the deflection also depends upon the magnitude of the current that flows. The magnitude of the current, more the magnitude, more powerful the wire becomes a magnet, and more force is experienced by the compass needle, and the deflection is almost 90 degrees. So this is about Oersted's experiment, and I think this is end of lecture number 1 over here. So first to digest this one, we have not started this chapter. We have just begun this chapter. Understand all these things, make a good notes, and henceforth I'll be rushing through a little bit faster rate, which are simple definitions and terms basically. So make a note of all this. Let us end this lecture and see you in the next lecture. Thank you for watching.